Hello everybody, we are here again with a new video on energy and its conservation. In our last video, we was discussing the conservation part with the help of this example, which I have said you in our last video. There's a glass jar, some water is in the glass jar and this glass jar plus water is kept on an oven. This was our system in our last video. And this room, wherever we kept our system, that room simply surrounds and we can take it as our surrounding. I have explained this part, the system and surrounding, in our last video. You can visit there and see it. I have said we are here to discuss the conservation part well. As I said you in our last video, the energy of the system and its surrounding is always constant. This is the conservation of law of energy. Whatever is our system doesn't matter, and whatever surrounds the system is simply the surrounding. Here we have taken this as our system, and in which room we kept it, this is our surrounding. The law of conservation of energy says that the energy of the system plus the energy of the surrounding is constant. And it will remain constant all the time. There may be the transfer of energy from the system to surrounding or from the surrounding to system. Because as we know, the energy can be transferred from one form to another form. So it must be transferred from the system to the surrounding. But the total sum of the total energy of system plus the total energy of the surrounding, this sum will remain constant all the time. Every time, each and every time. So we are going to do here this experiment. It's a small experiment and it will help you understand how energy conservation goes, or how will we find that how much amount of energy have transferred from the system to surrounding or from the surrounding to system. That's we are going to do here. We'll try to understand how it goes. Pause it for a moment.
Yes, go.
See, we'll do the experiment like this. We'll take our system. Initially, our oven was off. And the system is kept like this. How will we do the experiment? I am showing you. I am telling you. We'll start our oven, let the water heat up for some time. It will start boiling, maybe in 5 minutes or 10 minutes. After that, we'll shut the oven again and we'll see what happens. This is our experiment, and we'll try to calculate how the energy transfers. Initially, our system was off and this much height of water was in our vessel. Let it to be H1. This is just a random value, you can take anything. What will we see that after the experiment, means after the water gets boiled and we'll shut the oven again, we'll see that the height of the water in that vessel has been reduced. Say it H2, this is also a random value. Nothing else seems us to change, except that we'll feel some hotness if we are doing the experiment in that room, or while the water was boiling, you can put your hands on it and you can check that some steam is coming, some of the water has turned from the water form to the water vapor form. That also happens. How are we going to calculate this? As we know that since the water has reduced, this level has reduced, some of the water has turned from water to water vapor that goes to our surroundings, since we have taken the room as our surrounding. How will we calculate what amount of energy has been transferred from the system to the surrounding? Because the energy must have transferred, since there are some changes from our initial system to our final system. Let's see. What will we do? We know the energy has a lot of forms. Which form we'll use it here? As we know that some of the water molecules have vanished from our initial part to our final part. So we can try to calculate the kinetic energy of the molecules, but we don't know the velocity, because we know that kinetic energy is the energy that has to do something with the velocity of the object. We don't know the velocity of the water molecules, with which velocity they have started from here, or with which velocity they have gone to our surrounding. So we can't use the kinetic energy part here. Come next to the potential energy part. As we know that the potential energy has to do with the location of the object relative to something. So come here, can we use it here? Yes, we can use it here. Because see, initially our object, the water, has a location h1 relative to what? Relative to ground, if you take it as your ground. And finally, the location has changed. It has been s2, it has reduced. What happened?
Zero.
So we have seen it here that the location of the water has changed from h1 to s2 relative to our ground. So we can use the potential energy from the energy of the potential energy form here. Which potential energy form we'll use? Simply we'll use the gravitational potential energy form, because here this is our ground, or you can take it as earth. If you kept your oven or glass jar filled with water just on the ground and do the experiment, then that will be the earth. So you can simply use the gravitational potential energy. And what is the formula of the gravitational potential energy? Calculating it. C. To calculate the gravitational potential energy of an object, we simply do weight of the object into height. This is the height ascended or descended by the object. You must notice one thing here, that the gravitational potential energy is the potential energy of the object with respect to the ground. We take actually it is the energy of the object plus the ground as a combined body, but since the earth doesn't move with respect to this, it moves very little, so you can just neglect it. You can take it as a constant, then it will be the simply gravitational potential energy of this object relative to our ground. Positive. See, I have said you, initially our height was h1 before the experiment, and after the experiment, as we have seen that our height reduced to h2, then what happened? This part of water that was between h1 and h2 has been vanished somewhere in the surrounding. And you can think it in another way too. The another way is that this part of water is reduced up to a height h2. Since see, initially our layer was here at h1, finally our layer was here at h2. It shows us that the level of water, the upper level of water has reduced from a height h1 to h2. And similarly, if you take the infinitesimal layers of water, you can see that each layer has reduced its height from h1 to h2. So it shows that the water in the part between h1 minus h2 has reduced a height h1 to h2. So we need to calculate the weight of the water that was in this part and the height reduced from h1 to h2. We can use it if it was a solid object, the water, it was something like ball or box or something, then we can simply take the weight of the water and the height reduced. But since this is a fluid, it's a liquid, so we have to choose the integral way to do it, because that is the best way for summation of the things. The smaller part, if we take a very thin, infinitesimally thin layer, which we have taken the width of that layer at dz, it's a very, very small layer, infinitesimally small layer, then we can see that this layer dz has also reduced from this height h1 to h2. and see, we have done it here. The energy of that is that our infinitesimal part will be this dmg into h. Our for the dm mass of this infinitesimal part, this is rho. It's simply the density of water into the volume into this. This is gravitational constant, and the height is reduced. You can see here rho g. Since it shows our cylindrical vessel, so we can use it the pi r square L. It's the volume of the cylinder. So pi r square dz, and our height. We have taken this layer from a jet distance to the upper level of water. This is jet. You can ask me here that this layer is not at h1 and it's neither at h2. So how can we take it? We'll think some smartly, because we are doing here physics and some of the mathematics, so we have some common sense. We'll understand it well that this part of water has technically lowered its height from h1 to h2. So each and every part in this layer has reduced its height from h1 to h2. And to calculate that part, that height, we will follow the integral path that will give us the exact value. See, we have gone, this is our dE part. During the calculation you will get this, and the total energy that will be transferred in it will come this. And see here the sign of limit. Pause it for a moment. Take note here for the limit. As we were initially at the h1 height, and finally we were at h2 height, so we must take our integral from the lower limit of our integral was our initial point, so we have taken it as h1, and the higher limit, the upper limit of our integral will be our final point, that will be h2. We will integrate, since these terms are constant, rho, g, pi r square, these are all constant, so they will come out z dz, it will be z square by 2, and this term, it will come here. I need to write it in first part.
Yes.
Sorry for the interruption. Initially, as you have seen that I was missing for our limits, I have changed it because I have said you, this will be our initial point and this will be our final point. We always choose our limits of integral from our path taken. Doesn't matter where we are, but where we are initially, we took it as lower limit, and where we will be finally, we took it as our upper limit. That's why it was a simple mistake, I have changed it. So the total energy of that part will come like this, rho g pi r square, and this term, it will be in 2 with h2 square minus h1 square by 2. As you know from our figure that our h1 is greater than h2. So this will be minus sign. It happens rho g pi r square by 2. Pause it for a moment. We have seen that this is our result, but since in our figure h1 was greater than h2, so whatever value we'll take, even if it's in the square, when will we put the values, then we will see that this part will be greater than this, so simply a minus sign comes here, and this will be our final result. A minus sign shows that here our system has lost the energy, and that much energy has been gained by our surrounding. I need to write here, more space. Here that this energy is lost by our system. This is the lost energy by our system, and so this much energy must be gained by our surrounding. Since the sum of this energy of system and the energy of surrounding must be constant, so whatever we lose at one place, we must gain at another place, and whatever we lose, we gain at another place, we must lose it at one place. So this is here, our discussion is, I think, finished. And here I'll try to say you one thing, that we can, whatever our experiment be, it doesn't matter, but with each experiment we can make sure the energy of one part of our we'll do any experiment with one of our system and the other of our surrounding. So there must be one part from where the energy transfers to the other part. That never matters. Maybe sometime it transfers from system to surrounding, maybe sometime it transfers from surrounding to system, but the total sum must be constant. And this is the way to calculate. We have, as I have said you earlier, that we have several formulas to calculate this. Here we could have used other forms too, but since we have foreseen it that we can use the potential energy part well in it, so we have used this. There are some of examples. I'll come in the next videos and I'll show you that in those examples we can use the kinetic energy part. In higher physics or in modern physics, we have some parts that have to do with the chemical energy or atomic energy or maybe with nuclear energy. Whenever we'll go to the relativity sector, we can see that we have the rest mass energy. Rest mass energy is simply the energy that comes from your existence, from your sheer existence. Means if you exist in the world, then you must possess some of the energy. That is the energy associated with the mass energy. So I think this is sufficient for today. If you have any doubts, any problems, then you can ask me in the comment section. Thanks for watching.